Yes. Recording started and then okay. 1:45. Anyway, let us start. Oh, I have to share my screen. Yeah, do you see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay, thank you. Okay. Actually, my speaker was at a very low volume, so I was not hearing you. Anyway, fine. Okay, so let us start. Okay. Today, we will start with some exposure to so-called variables. So you have seen integer variables, floating point variables, and similar things. I will make the things clear syntactically and to some extent with respect to the organization of the data in computer's memory. Okay, but before going to the syntax, let us first understand that we are very much used to the decimal system. So this is basically a system of numbers written in base 10. What is so special about 10? The idea is that we have 10 fingers. Okay. So these individual fingers, this, they are called digits. Okay. So the 0, 1, 2, up to 9, they are also called digits. So we have 10 digits. Therefore, for us, it's a natural thing to use the decimal system, that is base 10 system. On the contrary, computer's world is binary. Okay. Typically, computers are built from a large number of switches, each of which can be in two states, on and off. So you may consider on as 0, sorry, maybe on as 1. Of course, this is also a valid thing, not a big question. You can take that also. On means maybe 1, off means 0. Okay. So this gives us two digits, 1 and 0. And using a sequence of such switches, we can represent any pattern of ones and zeros. Okay. So these are called binary digits. Because we are now going to use this in binary system instead of the decimal system. And as Claude Shannon introduced, this is abbreviated as a bit. So this BI and this T, bit. So bit was a term introduced by Claude Shannon. So electronics students will actually come across several pioneering works of Claude Shannon. Anyway, so introduced the term bit. Essentially, this led to the age of digital communication, digital representation. Anyway, so this was introduced in 1950s or maybe late 40s. Okay, so first of all, computer solved is binary. So in the last class, we may have seen things like 2, 5, minus 60, 2.3500. Okay, you have seen things like this. But all these so-called numbers and many other things, in fact, almost anything under the sun can be encoded in binary. Okay. With some standard encoding scheme, we can convert almost everything, even characters like A, B, C, dollar, hash. Okay. So I will start with a little bit of our understanding of encoding in binary, and then we will quickly switch to C data types. Let's first start with integers. For the time being, let us restrict only to positive integers or non-negative integers. In order to see that, every such integer has a binary representation. I give you an algorithm for doing it, but before that, let us see how many students are there. 161. 161. Not a good number for this example. Maybe I take 111. 50 less than that. Okay, and let us see. Any such number can be written as a sequence of bits, zeros and ones. So maybe I take 1, 2, 3. Okay, so this is in decimal. So I often write 10 as a subscript in order to make it clear that I am talking about the decimal representation. So this is nothing but 1 times 2 square, 2 times 10, or maybe you can call 10 power 1 plus 3 times 10 power 0. So 123 can likewise be written as a sum of powers of 2. 64, 32, 96 plus 16, 112 plus 8, 120 plus 2 plus 1. So this is 2 power 6, 2 power 5, 2 power 4, 2 power 3, 2 power 2 is missing, 2 power 1 plus 2 power 0. So now if I write it as a sequence of bits, am I correct? Ah, yes.
Yes.
Okay. Okay, fine. So this is 6, 5's position, 4's position, 3's position, 2's position, nothing is there. 1's position, this is there. 2's position, it is also there. So this is nothing but the binary representation of 123. In fact, how many bits have I used? 1, 2, 3, 4, 5, 6, 7. So this is called a 7-bit binary representation of 123. Okay. In fact, you can add any number of leading zeros at the most significant end, and the number does not change. So you can also consider this 1, 1, 1, 1, 0, 1, 1, and you have added 3 leading zeros. So this now becomes a 10-bit binary representation of the same number. Okay, but of course you require at least 7 bits, otherwise you cannot store all the bits. Okay. So for any number n greater than or equal to 7, you can have an n-bit representation of 123. Okay. So you just write any integer as a sum of the powers of 2. But the question is, how do I do it more methodically? Okay. So this algorithm is something like this: 123. You keep on dividing by 2. 61. And here you get the remainder of 1. This is correct, right? 122 plus 1. Again divide by 2. This becomes 30. The remainder is 1. Again divide by 2. 15. This is 0. Divide by 2. 7. 14 plus 1. Divide by 2. 3. 1. Divide by 2. 1. 1. Divide by 2. Eventually you get 0. Here you have remainder 1. So you keep on dividing the given integer, positive integer, by 2 until it reduces to 0. And you remember the sequence of remainders. You are dividing by 2, so the remainder is either 0 or 1. Okay. So in this case, it happened to be 1, 1, 0, 1, 1, 1, 1. Then what you will do, you simply read the remainders in the opposite direction as they are generated. So this is 1, 1, 1, 1, 0, 1, 1. Okay, so this is what is called decimal to binary conversion for positive integers. What about the opposite, binary to decimal? You simply look at this. 0 to power 0 is there. 1 to power 1 is there. Position 2, that bit is not there. 3, 4, 5, 6, these are there. 4, 5, 6. And if you do the maths, it will come out to be 123 with our popular decimal notation. Okay. So you can see that at least positive integers or non-negative integers can be represented by a sequence of bits. Now, what about if we consider the fractional part? Okay. So if we have something like this, 1, 2, 3.45.
Can you please tell again for binary to decimal, please?
Binary to decimal. Okay. So sorry. Consider this. Some A0, A1, A2, up to some AL minus 1. Each AI is a bit. This is the 0th position. Here the bit is 1. Second position, first position, the bit is 1. Second position, the bit is 0. So if I consider this in base 2, this is same as AL minus 1 times 2 power L minus 1. AL minus 2 times 2 power L minus 2. Keep on doing this. A2, 2 square. A1, 2 power 1. A0 times 2 power 0. So those bits which are 0, okay, this is the same as this, right? This times 10 square. Then this times 10 power 1. Finally, 3 times 10 power 0. Here in general, if I have a binary representation, a sequence of bits A0, A1, A2 up to L minus 1, then this expands to this number, this positive integer or non-negative integer. And since each AI is a bit, it is either 0 or 1. If it is 0, then it actually does not contribute to the sum. If it is 1, it will just contribute a power of 2 to the sum. Okay. This will contribute to power 0, this will contribute to power 1, this is not there, so to power 2 I do not need to consider, to power 3, to power 4, to power 5, to power 6. Add them up, whatever you get, this is the number in the decimal notation. Is that clear now?
Yes, sir. Thank you.
Okay.
Excuse
Okay.
me, sir.
Yeah, tell.
So we can write any number as sum of powers of 2.
Yes.
So how do we prove that?
How do you prove? Formally, how do you prove? Actually, this is a question not exactly related to this course. You may, for example, prove by induction. Okay, induction basis may be 0, 1, something like that. You know induction, right?
Yes, sir.
Okay. Then you consider, suppose the number is n. So you consider this 1, 2, 2 square, 2 cube, 2 power 4. So eventually n is a finite number and this thing is going to infinity. So there must exist some t such that n is sandwiched between this 2 power t and the next power. Convinced? So I have something
Yes,
like this. 2 power t less than equal to n, let's say less than 2 power t plus 1. Okay. So you know that 2 power t is there in n. Now subtract 2 power t. This is less than equal to 0. This is less than 2 power t. In particular, n minus 2 power t is smaller than n. Okay. And by induction, this can be written as a sum of powers of 2. And those those exponents, they cannot be t or bigger than t because the sum is less than 2 power t. Okay. So by induction, this can be written as a power of 2's, as a sum of powers of 2's. And then if I add 2 power t, I get a representation of n. And then, of course, there is a question why any two such representation must be unique. So you think about this, right? So this is a proof by induction. So far I have proved only existence. Everything can be done. Then what about uniqueness? Okay. So this proof I leave it to you. May I? Is this clear? You know induction, right?
yes, sir.
Okay, so this is the beginning of the proof. I have proved the existence of a representation of n, and uniqueness requires some more logical argument, mathematical argument to establish the uniqueness of a binary representation. Okay, so maybe I leave this part to you. Okay, fine. Okay, so that's an aside. Now let us see how we can have a binary representation of fraction. 1, we have seen 1, 1, 1, 1, 0. It will be point something something. Now this is no longer the decimal point, this is basically the binary.
This is not.
Yeah, do you want to say something? Otherwise, please switch off your microphone. It's creating a noise. If you say something, please go ahead.
Noise is not clarity. Background noise is.
Yes, sir, there is some background.
Yeah. Okay, I will mute. Okay, so I request you to mute yourself unless you are asking questions. Okay, when you ask a question, you just switch on your microphone and then switch off. Anyway. Okay, so in decimal, what is this? This is nothing but 4 times 10 power minus 1 plus 5 times 10 power minus 2 plus 6 times 10 power minus 3 and so on. Okay. So here also I can write things like this. If after the binary point 0 point B1, B2, B3 and so on, we can write it as B1 times 2 power minus 1, B2 times 2 power minus 2, B3 times 2 power minus 3 and so on, where each Bi is a bit, 0 or 1. Okay, so this can be done. So let's see how. Okay, so I tell you a procedure how this can be done. Okay, so let's start with 0.456. Okay, instead of dividing this by 2, I will keep on multiplying this by 2. Okay, so maybe I write it this way. Multiply by 2 and remember the so from this point multiply by 2, so what it will be 912. This is 0 point. If I multiply this by 2, so this 0 I remember separately. Okay. If I multiply this by 2, this will become 24, 1.8. So 1 I remember separately. 8. Again multiply by 2, I will get what? 48, 16. So 1 you just discard, but remember it. Then if I multiply by 2, 96, then 1.2. Again multiply by 2, this will be 92.50. Okay, multiply by 2 just once more. 1. Okay. So 0.456 is nothing but just read these things from top to bottom. 0, 1, 1, 1, 0, 1, and so on. Okay. Also, we know 1, 2, 3 is 1, 1, 1, 1, 0, 1, 1. And therefore, 1, 2, 3.456 will be 1, 1, 1, 1, 0, 1, 1, point, whatever you have, 0, 1, 1, 1, 0, 1, and so on. And this is an infinite binary expansion. Okay. So what is 456? 0.456 nothing but this by 1000. Okay. How can I simplify this? I can divide by 8, right? 57 by 125. Okay. So in decimal, this had a finite representation because this was a power of 10. Okay, so we have a finite representation if and only if the fraction can be written something like this: a over 2 power t for some t. Okay. Here it is not the case. Okay, it's 125 is not a power of 2. Therefore, this will keep on going until infinity. But anyway, as you have seen in the last 2 weeks program, that I am using something called float. Okay, float actually truncates this after a finite number of bits. Okay, so this you truncate after a fixed number of bits. So what you get is 11111011 point something 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 up to the point where you have truncated. So this gives you an approximate representation of the fraction, or for that matter 123.456. So I hope you now understand why.
So can you explain the 456 by 1000 is equal to 57 by 125? Can you switch off your mic, please?
Okay. Anyway, so you don't need to worry about too much about this conversion from one format to another, but I am telling it because you need to understand that in the binary world, everything can be done. Okay. So of course, if you think about 1 over 3, in decimal, this is 0.333, it will keep on going. Okay. And you cannot have a finite representation. So you have to truncate at some point of time. Just ignore the remaining things. So that will give you an approximate representation. Likewise, you could think about pi, square root 2. So after one point, you have to maybe after maybe after 10 digits, you simply truncate. So this gives you an approximate representation of pi. So in the binary world, the similar thing happens. Most of the things you cannot represent exactly unless it's of the form a over 2 power t for some t, for some integer a. Other than that, okay, you have to be satisfied with an approximate representation. Okay. In any case, you can see that whatever we do in decimal can also be done in binary without sufficient problem. Okay. So, yeah.
So how did you write 456 by 1000 is equal to 57 by 125?
Divide by this
Divided.
8. Divide this by 8. I just simplified this.
Sorry, could you explain
Okay,
once
yes.
again? 0.456 by 0.912. What will get, sir? I didn't understand. Could you explain once again, sir?
On multiplying by 2, and if you have anything moving to the other side of the decimal point, just remember it and neglect it. So this is 912, 0.912, just remember 0, multiply by this, it will become 1.824. Forget this one, but remember it. Okay, remember it, but for future calculations, do not use this one. Okay. Again, this is 1648. Just remember this one, but next time when you multiply by 2, don't worry about this one. So this way, you have a sequence of bits. You're multiplying by 2, right? You cannot have 2, 3, 4, 5 here. It will be either 0 or 1. It's a proper fraction. Multiplying by 2, you can have either
When
0. Yeah. Now, whatever you have, 0, 1, 1, 1, 1, 0, 1. Okay, so just simply write these things.
when we will write instead of in number na?
Now, what is the question? No, I didn't get your question. What?
Sir, I have one doubt. Sir, you have written there ki 2 to the power t. If the denominator is of the form 2 to the power t, then we will get a finite one.
Yeah.
Then, sir, how we will come to know that the decimal we have to end there? Means by twising the digit.
I'm not saying that you first find out whether it is of this form. So you follow this procedure. Multiply by.
Then, sir, how it will end? Because multiplying by.
Maybe you just end it after, let's say after 16 iterations. Okay. Okay, so I'll come to that.
Okay.
So after the finite number of iterations, anyway, you have to be happy with the finite number of iterations, finite precision of this. So you stop after that. Okay. So depending upon how much memory you have for your, for your real number. Okay. I only wanted to highlight that you convince yourself that integers as well as fractions can be represented by a sequence of bits. Okay. For fractions, we sometimes do not have any choice other than truncating this after a fixed number of positions as is required, okay, to store in a floating point variable. Other than that, so if this cannot be avoided. We cannot store an infinite sequence of bits. Okay, we cannot have enough memory for doing that. Okay. So anyway, so this essentially, okay, so this essentially gives you an idea that bit level representations suffice. Okay, maybe near the end of this course, we will, if we get time, I will give you a more detailed description of these formats. And we have not talked about how to represent negative numbers. Okay. Once again, you have I use bit to represent the sign. So 0 means positive, 1 means negative. Okay. And there are several schemes. If we get time, we will look at it. But for the moment, let us not worry too much about this exact representation schemes.
Hello, sir.
Yeah.
So what did you write after representation?
Suffice is sufficient. SUFFIC. Okay. Suffice means is sufficient. Okay. Okay. So That is the reason computers, not I would not say that is not the reason. The reason that computers world is binary because computers are built from a sequence of switches. We have to abandon our decimal notation and have a storage as a sequence, as sequences of bits. Definitely, when we supply a value or want to read a value stored in a variable, we like to have to see the decimal representation. Okay, so that kind of interface is provided by C. Okay. You specify things in binary, and there is a function that will convert that binary string to what is called a bit sequence. Okay, you don't need to worry too much about this. Okay, so we have first of all our numbers. So numbers include integers, whole numbers, positive, negative, 0. Then you have the real numbers. But here I have to accept an approximate representation. But anyway, here also there is a catch. Anyway, then you may also talk about complex numbers. So when we study so-called structures, we will see how we can represent complex numbers. Okay, because this is nothing but a pair of real numbers, a plus id. So if I can store a, if I can store b, I can store complex number. Okay, and so with this insight, let me tell you the basic data types of C. Okay, so first of all, int. This is positive, negative, and 0. And it is usually a 32-bit value. Okay, so this is the size. This is the range. And how do you input output? Okay, so integer, it's signed integer. It's in this range. Why it is in this range, this you will know later when we study what is called a 2's complement representation. It can be as negative as 2 power 31 minus 2 power 31, and it can be at most as positive as 2 power 31 minus 1. And when you use scanf to read an integer or use printf to print an integer, use this notation %d. And I think %i is also allowed. Okay, here D stands for decimal. Okay, so you are inputting and outputting in decimal. Okay, and I stands for integer. Both are allowed. Okay. As you can see, using a 32-bit space, you cannot store everything, right? At most 2 power 32 things you can store. So you have to accept this. Okay. And if you want to, of course, today's most computers are 64-bit computers. So in a 64-bit computer, there is something called a long int or long int. So this can store integers in the range minus 2 power 63 to 2 power 63 minus 1. Okay. And for IO, use long D or long I. Okay, L. Okay. But of course, if you use a 32-bit machine, long int may still mean 32-bit integers. They are actually, if you use long int, then you get 64-bit. Okay, the range is same. and this is, if I am not mistaken, capital LD. Okay. So you have seen examples, right? Reading and writing integers. I will give you, I will run several codes, okay, to illustrate how this IO can be done using these basic data types. Then you have float. So this is basically a 32-bit value, and range, let us for the moment to be specified later. Okay. And you read and write using %f. F stands for float. Okay. So like integers, you also have a 64-bit variant. So this is called a double precision floating point number. Okay. Once again, its size will be, the range will be discussed later. This is following this convention. This is %LF, long float.
Sir,
Yeah.
sir, what is the meaning of bit? Means because you have written previous example 123. Does that mean 3 bit? 1, 2, and 3.
Is a 3 decimal digit number.
And okay, so if we write 010, then that means 3 bit.
010 is a 3-bit number, and that number is nothing but 2. If you look at this 123, sorry, its decimal size is 3, but its binary size is 1, 2, 3, 4, 5, 6, 7. Okay. And here also I can include an arbitrary number of leading 0 digits. Okay. Here also I can append any arbitrary number of leading 0 bits. That doesn't change the number. Okay. So if you have 32 bits to represent this, then these 7 bits will be useful, and the remaining 25 bits will be just zeros. Okay.
So then what is the maximum number means we can find now from
Yeah,
these 32 bits?
That's the range. In
Okay.
This is the range. This is the maximum negative value. This is the maximum positive value. Okay. Likewise,
Sir,
if you
-1 is due to 0.
minus
1 is due to 0. We are considering 0 positive.
I don't understand your question. -1.
So 2 to the 31 minus 1. Yes, sir. That.
Yeah, this quantity.
Yes, sir. There is -1 because of we
Why
are
minus?
assuming 0.
Why -1? Because if you use 32
Yes.
bits, the first bit can be at least 0. Can take 2 values, 0 or 1. Second bit 0 or 1. Third bit 0 or 1. So total number of possibilities is 2 power 32. And if you start from here and end here and include that 0, you will see there are exactly 2 power 32 of them. Okay. Here also you can see there are exactly 2 power 64 of them. Okay, so this is about integers. There is another thing called unsigned integer. So if it is 32-bit, then you do not worry about negative numbers. Its range is 0 to 2 power 32 minus 1. Okay. So on the positive side, you gain a little bit. From 2 power 31 minus 1, you can represent it up to 2 power 32 minus 1. And this input-output thing is unsigned, U. And if you unsigned long or unsigned long int, this is 32-bit. And here the range is 2 power 64 minus 1. And like this, long unsigned. Okay, so I will give you several examples of
Sir,
doing input output with this. Tell.
Sir, what is the difference between long integer and long integer? All the properties are same. Then what is the
All the
meaning of
properties are
difference?
same. All the properties are same in a 64-bit machine. In a 32-bit machine, old machine, long int essentially means int. Actually, the C specification does not, I would pinpoint how this int will be. Okay. C specification says that int can be either a 16-bit or a 32-bit. Long can be either 32-bit or 64-bit, something like that. Okay. And when C was designed in early 1970s, making integer something like 16-bit saved a lot of memory. And at that point of time, memory was a very, I would say, costly resource. Okay. So people use 16-bit integers. But nowadays, memory is so cheap that typically use 32-bit integers. And even we have 64-bit machines, so instead of
Excuse me,
writing
sir.
long int, we can write just long int, 64-bit. Yeah, tell.
Okay, sir.
Hello, sir. Size long int size is 32 bit, but range is 0 to 2 to the power 64 minus 1. Why?
Yeah.
Sir, for unsigned long int,
Mistake.
as you have written.
Mistake. Just this is 64-bit. Yeah. Yeah. Thanks for pointing. Yeah, this is 64-bit. Like long, it is 64-bit, or unsigned long is also 64-bit in our modern computers. Okay, so what is TBSL? To be specified later. Because we have to understand something called the IEEE 754 format. If time permits, we'll do it. Okay. You can say it can
What
be
is
as
unsigned int?
unsigned means you are not considering negative things. Okay, so it starts from 0, you will never represent negative numbers. So that gives you a slightly better, I would say, twice the range in the positive direction. 2 power 31 minus 1 now becomes 2 power 32 minus 1. So you get twice the range in the positive direction. Okay. So but you cannot represent negative numbers in using this unsigned int or unsigned long int. Okay. So I just write one thing.
LU means
Yeah, tell.
percentage LU, sir. I mean,
Yes, sir.
U means unsigned, long unsigned. F means float, long float. D means decimal,
Hello, sir.
long decimal. Yeah, tell.
Sir, for unsigned int for 32 bit size, you wrote 2 to power 32, but for int and also size is 32 bit, but you wrote minus 2 to the power 31 to 2 to the power 31. Why you left 1 bit?
No. Just a minute. Let me light this. There is another data type. I will just. Its actual range is minus 128 to 127. And this is written like %C, character. And a character, I will demonstrate using several examples. Characters are actually A, B, C, D, $, and all these things. Okay. But each one has an ASCII value. Okay. They are essentially integer variables. Okay. Anyway, I will give you several examples. And you also have an unsigned character 0 to 255. Okay. It's unsigned variant. Anyway, forget about unsigned for the moment. Character, CHAR. It's basically a symbol. Yeah, so somebody raised a question.
In cat variable, sir.
Yeah, tell.
Hello, sir.
Yeah, tell.
Sir, in Can variable you used open bracket, that is we have not to include -128 and 127.
Mistake. I am an old man. I will keep on making such mistakes. Yeah. Inclusive. -128, 127.
Sir, what is the range of unsigned int? It is 231 minus 1 or 232 minus 1.
Size of unsigned long int is 64 bit, yes. In a modern 64-bit machine, yes.
Sir, in
Sir, char means
you left 1 bit. Why, sir?
like ABC, but why we are using the numbers, sir? -128 to 127. I did not understand.
I will come to that. I will come to that. Okay. For the moment, it's not clear, right? Yeah, I will come to that. So this is just a list of things. Okay. Normal things that we will do. Int, long int. There is something called short int. Let's not worry too much about short int because very few people use this. Let's forget about short int. Int, long int, float, double, unsigned. Okay, character. Okay.
Hello, sir.
Tell.
Sir, in int and long int, you did not include 1 bit. That is you 2 to the power 31 for 32 bit. Why, sir?
What is the question? No, I didn't understand your question.
We have 2 to the power 31 bits in the negative integers and 2 to the power 31 in -1 in the positive and 0. So total it makes up to 32 bits.
Right. Yeah. So this is 2 power 31. Negative things, 2 power 32 minus 31 minus 1, positive numbers, plus 0. So what is the sum? So this -1 plus 1, that will cancel for 0, then 2 power 31 plus 2 power 31, that will be 2 power 32. Okay. Why range is not this? This is once again for understanding why this is not done. You have to understand what is called a 2's complement representation. Okay, so I hope we will have time to go through this. Okay, so this is a standard thing in the so-called 2's complement representation. You will not understand. But for the moment, let us just accept this. So I hope we will have time to explain this 2's complement representation. Okay. That is why it is not like this. Yeah, something like this. Anyway, let's not worry too much about this representation because we have to code rather than understanding things. Maybe I will now switch to some examples. Oops. Okay, variables.c maybe. As I mentioned, you always have these 2 lines religiously, stdio.h, stdlib.h, and you have your main function. And last thing that I forgot. So you say exit 0 or return 0. Okay. Now the question is, how do I specify a variable? In C, whatever variable you use, okay, maybe I just mention a couple of things. How to declare variables. Okay, then I will see several examples. So declare variables. Okay, so it's something like type, name, comma, name, and another name, and so on. Eventually you say semicolon. Okay. So this type can be int, maybe long int, unsigned int, unsigned long int, you may have float, you may have double precision float, you may have character, and a few other things. Okay, and each variable is given a name. Okay, so anything cannot be the name of a variable or of a function. Okay, so C supports some kind of naming convention. Okay, so a name of a variable, okay, or of a function for that matter, can use only these letters, the lowercase Roman letters, the uppercase Roman letters, the numerals, and underscore. No other symbol may appear in the name of any variable or function, or for that matter, other names. Okay. More importantly, this cannot be the first symbol of a name. In other words, any name like that of a variable must start with either a lowercase or an uppercase English letter or by an underscore. After that, any sequence of these things may follow. Okay, so for example, these are valid names: A, ABC, A1, B2, underscore, yeah, underscore A, underscore 5. These are all valid C names. So these are all valid. What is not valid, for example, is A, B. Okay, you cannot have space here. 2A, B. This is not valid because it starts with 2. Okay, it cannot contain other things like A%B. The special symbols you cannot have in a variable. So these are not legal variable names. Okay. Okay. So type you have to specify, and then a sequence of names separated by comma and ending with semicolon is what you do. And each name must follow this naming convention. Okay. There is another restriction. A name cannot be a reserved variable, reserved word. Like a variable cannot be named int. It cannot be named float. So you cannot write int. Okay. So these reserved words you have to discard while naming your variable. Okay. Although int satisfies this convention, but this cannot be the name. Okay. So cannot be the first symbol. Also exclude all reserved words. Okay, so we will see. You can look at any I would say documentation on C, even our own slides. You have to find what are the reserved words, what the reserved words are. Okay, apart from these variable types, type names, you have some for, if, else. Okay, so these things cannot be variable names, although they otherwise fit in the naming convention. Okay. Okay, so let us see. I have, let's say, integer variables A. Okay. And I have, say, let's say, unsigned integer variable B. Then I have long integer variable Actually, long int you do not need to write. Unsigned long and D. So in C, you have to declare a variable, and every variable must have a type. Okay, int, unsigned int, unsigned long int, similar things. Okay. Maybe I need another window. Okay. So okay, what I will do, enter A. So this is just a prompt for the user. For reading, you have to specify, okay. Maybe I read all the things together, A, B, C, D, all the things. First one is int, so %d. Next one is unsigned int, %u. Next one is long int, %l. Li is not needed. Then one is %long int, unsigned long unsigned. Okay. Do not use spaces in between. Okay, that becomes what is called a formatted scanf. And although C does support it, I discourage you to do that. Okay, so use formatted scanf. And A, and B, and C, and D. Okay, so why not A, B, C, D here? Why do I have to write and here? Please wait. When we study functions, we will see that this and is necessary. For the moment, you just religiously follow the convention that before the variable name, you just pass an and. And is basically an address. Okay. So let me compile and let's see what happens. Okay, variables. Made a mistake somewhere. Oh, long, perhaps you have to write long decimal. Okay. Okay. Okay, so that's a mistake. So %l does not work, %long decimal. Yeah, tell. Have any other question? Tell. Okay, so in a scanf, if you want to read multiple things, you can do, but do not use spaces here. Okay. So then I will just run it. Okay, so A is your is an integer. So maybe -1, 2, 3. Okay. Then what is it? B is an unsigned integer. Okay. So for this reason, I have this 2 power 31 is this. I will just copy this. Or maybe I make it slightly bigger, 50. Then what is this long int? Okay. So maybe 2 power 50 is this quantity. And then I have unsigned long int. So 63. Again, I make it slightly larger. Okay, so it actually reads. But then if you want to print, use the same thing. A is B is what? Unsigned int. %u B. C is long int. LD. D is long unsigned D. Okay, so this is the syntax. So you specify within a pair of quotes whatever you want to print, and then whenever you have some %d, %u, whatever things, okay, these things will be read from after this quote. Okay. Okay, so let me get that out. Let me give the same value. Okay, so minus 123, fine. This also is exactly stored. This is exactly stored, yes. This one 810, this is also exactly stored. But let us see if instead of minus 123, I give this value, which is a little bit too big for integer. The remaining things let us keep as it is. Okay. So I entered this as A, but I see something like this. This happens because of an overflow. You cannot store this quantity 2 power 31. Yes, 2 power 31. Or actually, this is a little bit larger than that. Instead of 48, I have to. You can. This is too large for integer. So although I specified this, I am getting this value. Okay. And you can actually write a big thing like this here. We're getting something like -1. So other things are fine. 234, 367, 28. Okay. So it's necessary that you understand the. Okay, maybe this is a feature of the modern compiler. If it is too large, then it always says -1. But anyway, you don't have to rely on it. Okay. So what is important is that you understand that every variable has a range. If you enter a value beyond that range, outside that range, then whatever it stores, you do not exactly control. Okay.
Sir, why is -1 being coming as an output there?
Yeah,
like if it was unassigned int, then what would have been the output if our input value crosses the given range?
Yeah, you have specified something outside its range. So whatever it stores, you cannot control. You have given a bad value, and it has stored some bad value.
So is it some kind of default value or some kind of gibberish like it is?
I think there is nothing specified in the C and CC format. So different compilers do it in different ways. Okay, how to handle garbage?
I guess we will get a garbage value.
Yeah, it's basically you expect some garbage value or maybe something like -1. It's actually the, I would say the property of the compiler. Anyway, it's not a bad. It's a bad thing you have entered. So what the compiler does, you have to accept.
Sir, in my compiler, int and long int both have the same size of 32 bits. Means, is that an error, or I tried just now and I observed?
You have a 32-bit machine?
I'm not sure about that.
Oh. No, I said okay. So which is the operating system?
Windows 10.
Okay,
but
Windows. Again, I am not sure about Windows 10. So whatever I am saying typically pertains to Linux operating system. In Windows 10, it's very likely that it's very possible, even if you have 64-bit machines, you have 32-bit long int. If you want to use 64-bit integers, then you use long int. That is why I mentioned this. Yeah, if they are both 64-bit, yeah, in my machine, they are both 64-bit, but in your machine, this may be same as this. Okay, so long int may be either this or this. So if you are not, I would say, sure what your machine is, it's preferable to use long. Okay. You should force it to be a 64-bit thing. Okay.
Okay, sir. Okay, sir.
Yeah. Again, C specification does not make it clear. It's up to the compiler, up to the operating system, and all that stuff. Okay. Okay.
Sir, sir, why you are included the to printf and scanf?
Why?
In
What happened?
why you are command printf and scanf, sir? I didn't understand. I mean, we
What
are when we are writing program like we are using printf and scanf, but you are both are included now. In second case,
I don't understand. What do you mean? Okay, so these are the variables. You agree, right? A, B, C, D are some variable names that I have given. Okay. And then, of course, this is just a program for reading and writing. But after reading, you do something like area computation that we have seen in the last class. Okay, but here I am just specifying the scanf and printf formats. Does that answer your question?
I didn't understand, sir.
Actually, I didn't understand your question. That's why you cannot understand my answer. What's your question?
Okay, sir. Okay, move on.
Okay, so now I will do something with, let's say, floats. And maybe I just integer things you have seen, right? Let us do something with floats. A double B, let's say. And you see that you scan float by %f and double by %lf. Okay, sorry. Complete this and don't forget this and. This is one of the common errors at the beginning of programming. So also print A equal to %f, comma, B equal to %lf, new line, A, B. Okay, and let's see what it does. Okay, so I have not given any prompt. 1.24, something like this. Maybe I give the same or another thing. -2 point. Okay. So this looks like this and this looks like this. But as I mentioned, you can change, make a formatted. If I want 10 decimal digits, something like this. 10 digits. Can have right like this. Okay. Next one is, let's say, -9.123. Okay. You see there is a problem, right? 7, 6, 5, 6. Oh, here itself it changed. 3, 3, 4, 3, 2 is fine. 7, 6. Here it changed. 4 is 4 changed to 5, 5, 6, 2, 5, something like that. Whereas in the double, I have better representation. Okay. So actually, 32-bit floating point variables are a little bit too small to have a good precision. And we will see that it actually has something like 23-bit precision. Okay. So that's the reason this looks like an incorrect thing. So it's not 56. It's because of truncation errors. Okay. So if I, for example, use the same.
Sir, I have a doubt.
Just a minute. Let us see. 3, 3, 4, 3, 2, 7, 6, 4, 6, 2, 3, 4. Yeah. With double, you can have a better representation. Yeah. Now tell your turn.
Sir, in scanf and printf, we can use either of them, no? I mean, we should use only one.
No, I don't understand the question.
सर जो आपने scanf भी लिखा है और printf भी लिखा है, I mean we will use either of them, no? एक ही use करेंगे ना उनमें से?
No, this is for reading. This is for printing. User will enter some value here. Okay, so as I am doing, and whatever is stored. Yeah, tell.
Sir, in printf we can use %f and %fl also. Then why you used separate scanf?
What is the question?
Sir, in printf we can use %f and %lf like that.
Percent? Is that you mentioned just I do %f? Is that your question?
Yes, sir. Then why you used scanf?
Exactly. So if I use %f, let's see what happens. Good question. Let us give this same value. Okay. I see. Okay. I am not sure. Maybe it is just doing an automatic typecasting. Okay, so let us do one thing. B equal to %f. Percent, what is that? 10 LF. So you are reading B, you are printing B twice. Okay. And you are using this value, maybe this one. So there are two readings. Oh, I see. I should print something like this. Where was I getting an error? Oh, this is erroneous thing. Okay, let us use this. No. This was the value, right? Yeah. A little bit. I'm a little bit surprised that this is printing correctly. Little bit surprised, but definitely for reading this will not. This is not a good idea. But why it is doing it correctly, I'm not exactly very sure. Anyway, and also I'm not getting any warning message. Anyway. So let us see. What happens if I do this thing here? Okay, so now you see that there is a warning message. Format %f expects arguments of type float star, but argument 3 has type double star. So I hope this is compiled. Now let us see if I enter these values. Okay, now you see there is a problem. Right? B is not properly read.
Sir, for V you have to use %LF, but you use the %F.
Yeah, that's the reason I'm showing you. In scanf at least it matters. But I expected that this will also matter during printf, but that's not happening. This is for a reason not exactly very clear to me. Okay, so this LF is actually necessary. This is fine. For printf also I believe it is necessary, but there may be some esoteric situations where this will matter. So I have to work it out. Okay. Anyway, so now what remains is I will explain the read and write of characters. Okay. And a little bit about constants. Okay, so what is the time? It's 4:30. So can we have a just 5 minutes break?
Yes, sir.
Okay, so let us just have a 5 minutes break. It's difficult to talk.
Thank you, sir.
Yeah, tell.
Sir, why you have written %.10LF?
Okay, because I wanted to print, you see here, 7656250000. I wanted to.
Why that .10 is written?
Why?
.10 before
Yeah,
F.
you see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After the decimal
Okay,
point,
sir.
I have read. I wanted to print 10.
Okay, sir, I got it. Thank you, sir.
Okay, so you can write bigger things there. Let us see. You can write something like 20. No, not this one. Okay. So again, you can see that there are certain chunks there. So, okay.
Excuse me, sir.
Yeah.
Sir, if we don't write that 0.20, then it won't able to give us an output.
Yes. It will just be, maybe it will give. It depends upon the compiler. Maybe just 6 digits or something like that. Okay. Let us see what happens. Oops. No. Okay, so default behavior in this machine is 6 digits. Okay, so I will just take a 5-minute break. I'll come back. Hello.
Yes,
Yes,
sir.
sir.
Yeah,
Yes, sir.
Yes, sir, you are audible.
yeah, fine. So let us see a little bit about characters first. Then I will explain certain things to you. What is called constant. Okay. Let us have two character variables. Sorry, A and B. Or maybe I use some CH1 and CH2. You want to scan %C, and never forget this and. Printf.
Hello, sir.
Yeah, tell.
Instead of C, percentage C, we are putting percentage S. Is there any problem, sir?
Percentage is something different. Let us wait a little bit, because I have not talked about all the data structures. Percentage is for reading strings, not characters. Okay.
Okay, sir.
Okay. %C and character 2 equal to %C. Percentage we will look at later. For printing, you do not need any AND. Okay. So you entered character 1 equal to %C. This will be read from here. And CH2, this will be read from here. Okay. And let us see what happens. So I enter A and B. Okay. So you see that this is not performing correctly. It should write B here, right? Yes or no? But it's just printing nothing here. Actually, it is printing something.
Space.
Yes,
Space, sir.
in space. So space is not part of a float or an int, unsigned int, double. Okay. But a space in its own right is also a character. Therefore, if you actually want to see what it is printing, so you just write something like this. Okay, if I want to print a quote, I have to say \quote, \quote. Now if I say AB, okay, so you see character A is this, character 2 it reads as this. Okay, so space is a valid character, although it's not a valid integer or a part of a valid integer or double precision number or other things. But so you should be careful. This is very important. So if I want B to go to CA character 2, I should not use any space. Now things are fine. Okay. Again, you can see if I just A and just return, then this starts here, ends here. So this new line character, this is also a space, sorry, also a character in its own right. Okay, so it actually writes the beginning quote and this new line, which is actually invisible to your eyes, but it is there. Okay. So be careful when you read characters. Is it
Excuse
clear?
me, sir.
Yeah, tell.
Sir, why does it not print space B in character 2?
Where? This
Sir,
example.
in means the third one means if we write A space B, so it prints A in first one, character 1, then why does it not print space B in character 2?
No. Space is a character, B is another character.
Sir, why does it print the quote after the new line even though you put the \quote before /n?
Oh, you just asked, I didn't enter this. After A, I simply hit a return. Okay. So this A is read as the first character. Okay. And then I have a new line thing. And that new line is again a valid character. That is read as the second %C. Okay. So in C, and for that matter in almost any programming language, you have, okay, maybe I precisely mention what is called ASCII.
Sir, you are not audible.
I'm not audible. Why?
No, sir, you are audible.
Audible, sir.
Okay.
Audible, sir.
Okay, maybe at that point of time I was not speaking. So this is American Standard Code for Information Exchange. Okay. No, American Standard Code for Information. This I is what? It's actually not exchange. Information. I do not remember. Information. What that thing? So you can find out from Google.
Sir, it's interchange, I think.
Interchange. Yes, not exchange. It's
Yes, sir, interchange.
interchange. Good. Yeah. Okay. So every character that you see, space is sometimes written like this. This has ASCII code of 32. Then you have something. 0 starts at 48. You don't have to remember these things. Why? I will just explain. 49, 2 is 50, and so on. 9 is 57, and there are certain things there. I do not remember the entire table. Then the capital A starts at 64, B 65, and so on. Z becomes what? Capital Z, 64 plus 26, 90 minus 1, 89. Then there is something, A starts at, small a starts at 97 or 96. But maybe I am wrong.
I think capital A starts from 65.
65, 66, this is 90. Yeah, this is 97, B is 98, and small z is how much? At
122.
122, right? Yeah. Okay, so 32 to 127. In this range, you have the visible characters or standard characters. The exact ASCII chart you can ask Google and it will show you. Okay. And this new line character, if I am not mistaken, this is something 13. Okay, something like that. 13 or 9 or something like that. Okay. Or maybe tab is 9. Okay, so let us, we can actually demonstrate this. Let's do only one thing. Just read one, character 1, and I will just say character 1 is this. Okay, sorry, %C. Its ASCII value is %D. Okay, so you are essentially printing a character as an integer. I hope this will not be a problem. If there is a problem, I will repair it. Let's see what happens now. Let me just compile it. So A. Character is A, its ASCII value is 97. Then you just say space. Space has ASCII value of 32. Then you just print percent. Percent, where is percent? Yeah, this one. Percent's ASCII value is 37. Okay, so this way you can actually get the ASCII values tab. I will put tab. Tab is 9. Good. And I just say return.
Sir, if you just hit enter.
Yeah, returns ASCII value is 10. So I made a mistake. So it's not 13. So new, this one is not 13. This is 10. Yeah. And then you have other things like control A. Let us see. Its ASCII value is 1. Okay. So some such peculiar things you will find before 32. Okay. But anyway, don't worry about this. You tell another character. Zero is 48. You can see. At the rate is 64. Let's see what is AND. It is 38. Okay. So this complete ASCII chart you will get in many places. Okay. So in fact, these characters are actually integer variables. Only thing is that these are 8-bit integers. You can add 2 characters, subtract 1 character from another, and so on. Okay. So, but be a bit careful when you do things like this. Space is a valid character. Therefore, first %C reads this A, the second %C reads the space, and it prints this, which is apparently invisible. In order to make it visible, I have used 2 containing quotes. Okay. So that covers most of the basic data types, integers, floating point numbers, and characters. We will later see how to play with 2 other fundamental data types, character arrays, which are called strings, and so-called pointers. Okay, anyway, let's not worry too much about this. When time comes, we will.
Excuse me, sir.
Tell.
Sir, the ASCII, we have the ASCII table. It contains 128 different characters. So when we are using char, we can use the ASCII. I mean, we can print the ASCII value for different characters like that. But in case of Unicode, how will we print it with char? I mean, the char has.
C as such does not provide any facility to handle Unicode. So you have to play with Unicode using something else, some editor level commands or things like that. Unicode is not supported by C, as far as I know. Okay, if some recent version does something like %LC and all that stuff, I do not know, but for the moment, let's say that %C handles only 8-bit characters, not Unicode.
But then we.
Then? Yeah, we follow Unicode, but C as such, at least in the %C format, it does not support Unicode. So how it supports, if it has any support at all, then I exactly do not know, to be very precise. Okay. So ASCII table somebody has found out. Good. Anyway, so you don't have to remember this thing. In fact, what I will now do, character for ASCII value. Let us do something. Let us put some integer n, let's say 45. Character for ASCII value %d is %c. N. Let us see what it does. For 45, the ASCII value is minus hyphen. Okay. So characters are also integers. Don't get confused. So whatever you see in that ASCII table, that integer part, that is precisely associated with A, B, C, minus, space, all that stuff. They are integers in their own rights. They are called characters because they look different here, right? So this H, this is basically identified with its ASCII value. This forward slash, this is identified with this ASCII value. Now, when I say print these ASCII values in this form, in this font, it will print something like this. And if I change the font to something else, they will look differently. Right? Okay, but let's not worry about Unicode.
Sir, then the at the machine level, when it does the computation, it changes the ASCII value into their respective binary values, and then it works on that when using characters.
Look, a computer never stores anything other than bits. Okay. Although you enter this at and hash 123.456, when it comes to the issue of storage, everything is a sequence of bits. So when it wants to store this character 2, it converts it to the ASCII value 50 or whatever its binary representation is, 8-bit binary representation is. So 32 plus 16 plus 2, whatever it comes. Expand that to some 8-bit value. That is stored. That is the reason I mentioned the computer's world is binary. It only stores zeros and ones. How you interpret your zeros and ones, that is up to you. Does it answer your question?
Yes, sir, it does. Thank you, sir.
Okay. Now you see that I have already done one thing. During the declaration of a variable, I have initialized n to a constant value. Okay. So this you can do. So I can say n equal to this or m, comma. So m is not initialized, but n is initialized to 45. And let us see some other, maybe double. Fraction 1.234. Second fraction I am not initializing. Then I have character C equal to character constant is this. Enclose within single quotes, not double quotes. Okay, and D is, let's say, just 2. Okay, so let me one by one print these things. M is not initialized, right? So you want to expect some garbage or something like, maybe it depends upon my machine, whatever is there in the memory. Okay, so now, so I have used double F and G. Percent, this is long double, right? So it's preferable to use LF, although we have seen that percent F is also working. G is not initialized, so you should get some junk value. This is float, F and G. What did I use? C and D. C equal to, within quotes, percent %C, and D is within single quotes, percent %C. Where is it? This new line, C and D. Let us see what it prints. Okay, so because I have used this minus W all flag, it gives me the warning that M is used uninitialized and G is used uninitialized. So if I, yeah, do not give this minus W all option, then it does not give me these warning messages. So you see that W value is always a good option. It actually gives you some idea that M is used uninitialized. So that's the reason I always prefer compiling with the W all option. Okay. Anyway, let's see what happens. As AM, you get some junk value, 21956. From where it is getting, I don't know. N is anyway, I have initialized to 45, so it's printing correctly. F is 1.234, that is what I have done. G is again uninitialized, you can see anything here. C is 2, character 2, and D is something whose ASCII value is 2. Okay, so maybe I will, instead of 2, I will use 9, because 9 is tab. We know that. Okay. Okay, now you see that this M value has changed, 21956 to 21909. You cannot rely upon it, whatever it stores. It may be anything. Okay. And this quote 9 is the character 9, whereas this just 9 is the character with ASCII value 9, which in this case is the tab. Okay. Happy or no?
Excuse me, sir.
Well,
Sir, actually, I didn't get this program. What are you trying to get as output, sir, in the program which I am explaining now?
This one.
Yes,
Yeah,
I didn't get that properly.
No, idea is that I have initialized N during declaration to 45, but N is not initialized to anything. So it can store anything, any garbage value. Okay, so you cannot rely upon that. Here I have explicitly initialized F during declaration to 1.234, but G is uninitialized. So whatever it prints as G, you cannot rely upon this. And this character, I have initialized both. And for the case of C, I have initialized to the character constant 9. So this is 9. Whereas this D is initialized to 9, not character 9. It is to the character whose ASCII value is 9. And that happens to be the tab we have seen, right?
Yes, sir.
Okay. Okay, so it's very difficult to, explain everything. So eventually you have to write codes yourselves and make things clearer. Okay. So definitely I cannot cover the entire C manual during these lectures. Also, it is too boring. Right. So it's already past 5. So you can see these are constants. Integer constants are like this. And let me explain another thing. There is another way of specifying double precision formats. What do you think this G is?
Avogadro constant.
Avogadro's constant, right? Yeah. And M I can actually, okay, M also I can do something to illustrate. Minus 0x 1, 2, 3. Let us now see what happens. Now, of course, the compilation will be happy. Okay. So it has actually expanded like this, 6.023 10 power 23. It is actually expanded like this. But if you wanted to write it in this form itself, you can use this. Instead of F, use E. Okay, 6.023 times 10 power 23. So this is the scientific notation. E stands for the exponent notation. Okay. This way also you can specify floating point constants. And what did I do when I wrote something like this? Minus sign is fine. So minus sign is here. So what is 0x123? Any idea?
After
Yes, please.
hexadecimal.
Hexadecimal. Okay. So if you start an integer constant, in this case, let me explain why it is like this. So if you start something 0, x, 1, 2, 3, these will be treated as hexadecimal digits. So hexadecimal is nothing but base 16. So this is constant notation. In our mathematical notation, this is nothing but this 123, 16, which is 1 times 16 square, 2 times 16, plus 3 times 1 basically. Okay, 16 power 0. It's 256, 32, 3. This is 293. Okay. That is the reason it has printed. Sorry, 291. 256, 32 is 288, 291. And if you want to see it in hexadecimal, you print as %x or %capital X. Let us see what happens. Maybe this is the last thing for today. So why is it like this? %x, why is it? Oh, I see. Is %x always pertain to unsigned integers. This looks like unsigned integer. Percent x pertains to unsigned integer. Okay. So in that case, I should not write. Yeah, percent x. So you can see it is not like 1, 2, 3. Okay. So if I give a positive value, then you can of course see the correct thing. Yeah. And what is D? So hexadecimal requires how many digits? It is base 16. So you have 16 digits, hexadecimal digits. Up to 9, this is fine. Then you have 10, 11, 12, 13, 14, 15. 6 extra digits. This is written as capital A or small a. This is written as capital B or small b. Likewise, C, D, E, F. Okay. Percent small x means use small a b c d e f. Percent capital X means use capital E a b c d e f. And what is 45? 45 is 2 times 16, 32 plus 13. So this is 2, and what is 13? 10, 11, 12, 13, A, B, C, D. This is 2D. Hexadecimal. Okay. Yeah, so there are many such small things, but the basic idea, I hope we could explain how to declare variables, types, give proper names, and you can initialize during declaration using constant values, and you can read and write using scanf and printf using these percent things. Okay. Yeah. So I think that's all for.
Sir, in the previous output, how did you get that combination of F, E, and D? I mean, you took F 0, X 1, 2, 3. Then why did that output come for them?
No, percent x is for printing only positive numbers, unsigned numbers. So you figure out. I do not remember actually. Is there a way of printing signed hexadecimal numbers? Ask Google. Let's see what it says. Signed hexadecimal. Percent what? So then we can explain. Let's find out if there is a way to do it. I can also make a search.
Sir, on Stack Overflow, people are telling that there is no way to print if a signed hexadecimal number.
Oh, then there is no way.
In C.
Okay, then there possibly no way. Yeah. Maybe, or maybe it is there. So don't treat this Stack Overflow and all this thing as the ultimate word. So read some book. I mean, some standard NCC textbook. They will possibly give you a better answer. Anyway, whatever it is. So I hope the following things are clear today. So tomorrow we will start with something else. So I hope we could cover these things, variables and their declaration, even their initialization to constant values. And read and write. Okay, so there are a lot of things that I did not mention, and it's impossible to mention in this small 2 hours or 3 hours or something like that. For that, you please consult a textbook on C. Okay. I hope I have given you sufficient exposure to do all practical things in your labs. Okay. And those fancy things you just read from, I would say, textbooks or manuals or something like that. Okay, so next day we will talk about expressions and assignments tomorrow. Okay, so which textbook? Last week I mentioned, right? The good thing maybe your Gottfried, or you can read Balaguru Swami. Yeah. Percentage to print hexadecimal values. Yeah. Not for signed, yes. Anyway, you figure out. I do not know. I have to do this kind of little bit of search. Okay, so shall we end the meeting? It's already 14 minutes past 5.
Thank you, sir.
Thank you. If you have any question, you can shoot. Otherwise,
Thank you, sir.
Anyway, you're going.
Thank you, sir.
Thank you, sir.
Okay, so see you tomorrow.
Thank you, sir.
Thank you, sir.
Bye.